Okay, finding and evaluating inverse functions. So write the inverse of each relation. So if we're given like a discrete list of points, what we want to do is we want to interchange the x and the y. So 1, 5 is now 5, 1. 3, 2 is now 2, 3. Negative 7, 4 is now 4, negative 7. And 3, 0 is now 0, 3. Okay, so this will be f inverse, f at x inverse. And so it's like f raised to the negative 1, but that's not an exponent. It's just the notation for the inverse function. Okay, so if this is f at x, we're going to go f inverse at x. If we want to do this in mapping as well, what we're going to do, maybe I'll write the numbers first. We're going to switch the x and the y. Okay, so the domain becomes the range becomes the domain. So 1, 6 is now going to be the first oval in the mapping, and then negative 4, negative 2, 2, and 5. Negative 4, negative 2, 2, and 5. Okay, so our mapping's set up. Now, negative 4 mapped onto 1, so 1 is now going to map onto negative 4. Negative 2 mapped onto 1, so 1 is now going to be mapped onto 2. Negative 2. 2 mapped onto 1, so 1 is going to be mapped onto 2. And 5 mapped onto 6, 6 is now going to map onto 5. Okay, so then this is the f inverse of x. So for number 2 is asking us, are these functions? So what we're doing for a function is we're looking if x is mapped onto only one y. Okay, so in the first f inverse of x, the x values that we have are all different. 5, 2, 4, 0. So that is a function. So let's write function. Okay, now 1 maps onto negative 4, negative 2, and 2. Remember, if more than one arrow is coming out of an x value in the mapping, it is not a function. Okay, number 3, sketch the inverse graph of each of the following functions. So something like this, I would actually take a look. So this, I like the points. So negative 4, negative 2 would then map onto negative 2, negative 4. Okay, we're going to connect that with negative 3, negative 3. So we're going to connect that with this. Oh, I see what I did wrong. Sorry, negative 2, negative 4 is here. That looks better. Okay, and then negative 3, negative 3. Because this point lies on the x equals y, like we can see x clearly equals y, that point's actually not going to switch because it actually lies on that line. So it's going to have the same two numbers. Okay, so I left off here. So 0, negative 3. I'm going to map onto negative 3, 0. Okay, and then 6, 1. I'm going to map onto 1, 6. Okay, and we can call that f inverse at x, if this is f at x. Okay, so if this one's f at x, let's choose a couple points and let's reflect it. Okay, so I'm going to choose like x-intercept. So negative 2, 0, 0, negative 2. Okay, 4, 0, 0, 4. Let's do the vertex, which is 1, negative 9. So we're going to go negative 9, 1. And then we can go ahead and we can connect these, and this is going to be our f at x, f inverse at x. Okay, let's make some room. Okay, so now let's work on 4. So given h at x equals 2x plus 7, we're going to just find for a the inverse. So when we have h at x equals 2x plus 7, we can't find the inverse with function notation, so we're going to sub it in for y equals 2x plus 7. Now we're going to actually flip the spots where x and y are. So we have x equals 2y plus 7. Now let's rearrange. We'll bring the 7 over. It becomes negative 7. And we're going to divide both sides by 2. So I get y equals x minus 7 over 2, but this is actually y inverse. Okay, so then we substitute back in the function notation f at x inverse, or f inverse at x equals x minus 7 over 2. So for b, we're just straight substituting in h at 3. So we have h at 3 equals 2 times 3 plus 7, which is just 6 plus 7, which is 13. Okay, this time we're going to sub in h inverse at 3. Oh, I put an f here. This is supposed to be an h. So h inverse at 3 is going to be 3 minus 7 over 2. So I get negative 4 over 2, which I get negative 2. Okay, and then D, we're going to do h inverse at 9. So again, I'm going to take h inverse and I'm going to substitute 9. So 9 minus 7 over 2, I get 2 over 2, which is 1. Okay, number 5, if f at x equals kx cubed plus 1, so they're giving us this piece of information, f at x equals k x to the 3 plus 1, and they're giving us that f inverse at some number 15 equals 2. We're going to have to find k. So because they give us this ordered pair, and remember this is the ordered pair 2 comma 15, no, 15 comma 2, did that wrong, 15 comma 2. The reason why it's 15 comma 2 is because it's f at x. So this is clearly going to be the x value. Okay, what we're going to have to do is first, because this is of the inverse, we're going to have to find the inverse first of f at x equals kx cubed plus 1. So let's first substitute in y. So kx cubed plus 1. We can, let's switch the x and the y's. X equals k y cubed plus 1. Okay, and now we just rearrange. So x minus 1 equals k y cubed. And then we can divide both sides by k. So we have y cubed equals x minus 1 over k. Now, in order to get rid of the cubed, we have to cube root. Okay, don't square root, make sure you cube root. So we have y equals the cube root of x minus 1 over k, and we can change this back to function notation. So f inverse at x equals the cube root of x minus 1 over k. So all we've done so far is find the actual inverse. Now they give us this information. So if we substitute the y in with a 2, and then we do the cube root of x, which is 15 minus 1 over k. What we'd have to do here is isolate and solve for k. So in order to get the cube root off the right-hand side, we have to cube both sides. This cube root and this cubed go away. So we have 8 equals 15 minus 1 over k. I'm going to cross multiply the k up, so we have 8k equals 15 minus 1. Okay, so then we have, divide both those out by 8. We have k equals, 15 minus 1 is 14 over 8, and we can simplify that to 7 over 4. Okay, so the k value is 7 over 4. Okay, number 6, we're given another line. Given f at x equals 3x plus 2, we're going to first just find the inverse. So f at x equals 3x plus 2. We're going to substitute in for the function notation. So y equals 3x plus 2. We're going to switch the x and the y. So x equals 3y plus 2. And now we can rearrange and solve. Okay, so x minus 2 equals 3y, and we divide both sides. So we get y, and it's going to be y inverse, equals x minus 2 over 3, and we can rewrite this as f inverse of x equals x minus 2 over 3. Here is the inverse function. Okay, b is a little bit different. We have to show that if we were to substitute the inverse into the actual original, that we're going to be just left with x, which makes sense because we would be left with like the y equals x, or y equals x, that's the reflection line. And then also it's like the step right here where we switch the y and the x. Okay, so that all makes sense. So let's substitute this equation in for the original. So we have f at x is 3x plus 2. So if we were to actually sub in, so f at x minus 2 over 3, what would that look like? So we'd have 3x minus 2 over 3 plus 2. Okay, take a look at this. These 3's cancel out. We're left with x minus 2 plus 2. Those two cancel out, and we're left with x. So what this is telling us in like real life is that when we apply an operation or a function to a number, and then we apply its inverse, we actually reverse that. I'm going to give you an example. Squared and square root are inverses of one another. So if I gave you 5 squared and you get 25, and then we go ahead and root the 25, we're going to get back to our original, which is 5. Right? So if you apply squared and then square root, those actually cancel out and you're back to the original. Okay, 7a, find the inverse equations for the following. So f at x here is just a line. Okay, so we're going to go through those steps. We're going to first sub in y for the function notation. Then we're going to switch the places of x and y. We're going to rearrange. Okay, divide out that 3. And we're left with y equals x minus 2 over 3. Okay, so f inverse at x, in this case, is x minus 2 over 3. So the inverse of a line is also a line. Okay, now b. We have g at x equals 4x to the exponent 5 minus 3. So let's substitute in y equals 4x to the 5 minus 3. We're going to switch the places of x and y. And then we're going to rearrange. So we have x plus 3 equals 4y to the 5. Divide both sides by 4. We have y to the 5 equals x plus 3 over 4. Now, in order to get rid of the y to the exponent 5, we have to fifth root this so that those two cancel. Okay, so we're going to fifth root this. We're left with y equals the fifth root of x plus 3 over 4. And then we're going to rewrite back with function notation. Even if the inverse is not a function, we still write it with function notation. So we get g inverse at x equals the fifth root of x plus 3 over 4. Okay, so we can see the inverse of x to the 5 is the fifth root function. Okay, so C. We have a rational function here. We have h at x equals 1 over x minus 2 minus 2. So the first step is to substitute in for that function notation. We're going to have y equals x minus 2 over 2. So now we have to switch the x to the y. So we have x equals 1 over y minus 2 minus 2. Okay? So now we have to rearrange and solve for y. So I'm going to bring that 2 over. So I have x plus 2 equals 1 over y minus 2. So here's what actually happens here. I'm going to group the x plus 2, and I'm going to group the y minus 2. And I'm going to cross multiply. So I'm going to multiply this up here. Y minus 2, x plus 2. Please do not expand, because you're going to end up mixing up like x times y, and it's going to be more difficult to get rid of. But now what I'm going to do is I'm going to divide out by that x plus 2. Okay, so far we have y minus 2 equals 1 over x plus 2. Then I'm going to bring this over, and we're left with y inverse equals 1 over x plus 2 plus 2. Now, the last part is to substitute back in that function notation. We were dealing with h. So we're going to go h inverse at x equals 1 over x plus 2 plus 2. Okay? On that, you can state the restriction, x cannot equal negative 2. Okay, now we have d. So d is g at x equals 3x squared plus 18x minus 7. So here's the thing with this. We actually can't find the inverse when we have an x squared and an x. So what we have to do first is we have to complete the square. So we have to bracket the two first terms and factor out that 3. We get x squared plus 6x. Okay, we have to take that middle term, which is 6. We divide it by 2, which is 3, and then we square it, which is 9. Okay, so we have g at x equals 3x squared plus 6x. Then in this bracket, we're going to add 9 and subtract 9. Okay, and this negative 9 comes out. We multiply it by that coefficient 3, and we're left with 3x squared plus 6x plus 9 minus 7, and then 9 times 3 is minus 27. Okay, so g at x equals 3. We're going to factor this, x plus 3 squared. Okay, remember this is going to be a perfect square trinomial, and then minus 34. Okay, at this point, we have it 1x on the right-hand side, and then essentially we have a y on the left-hand side, and we can go ahead and we can find the inverse. So we're going to switch the x and the y, and then we're just going to rearrange and solve. Okay, so we're going to bring over this 34, and I get x plus 34 equals 3y plus 3 squared. Okay, divide both sides by 3. I get x plus 34 over 3 equals y plus 3 squared. Okay, so what we do to the right-hand side, we do the left-hand side. So we're going to actually root the right-hand side, and we're going to root the left-hand side. So I'm going to switch these. So I get y plus 3 equals the root of x plus 34 divided by 3. Bring that 3 over, and it becomes a negative 3. So I get y inverse equals x plus 34 over 3 minus 3. Okay, we want to substitute back in that g at x notation. So g inverse at x, and then I'm just going to copy down exactly what I have. So here's the thing. Because we're going from a quadratic to a root function, we actually have to take into account this plus minus option. So if we only took into account the plus option, we would only be taking into account this one leg, or like this one side of the parabola. And if we only took into account the negative option, we'd only be taking into account these two. So in order to get a full parabola, we need both the left and the right arms. So we have to take into account both the plus and the minus options. Okay, so we're on E. We have f at x equals the square root of x minus 5 minus 4. Okay, so we're going to go ahead and substitute in a y for the function notation, x minus 5 minus 4. We're going to switch the x and the y. So we have y minus 5 minus 4, and then we can rearrange and solve. So bring that negative 4 over. We have x plus 4 equals the square root of y minus 5. We're going to square both the right-hand side and the left-hand side. So when I say that, I put the left-hand side all in brackets, and I square it. We're left with y minus 5. I always seem to bring the y over the left-hand side, like switch the places at this point. And then we have x plus 4 squared. Okay, let's bring that over. We're left with y inverse equals x plus 4 squared plus 5. And we can go ahead and substitute back in that function notation. Okay, so here's the catch about this one. The original, right, started at 5, negative 4. So 5 and then negative 4. And then there's no reflection, so that's what it looks like. There's just like a shift to the right and down. So here's the issue with our parabola. Our parabola, the vertex is negative 4 and 5. So negative 4 and 5. So this is what we're stating that our vertex is. Our inverse. But that's not our inverse, because if we were to take a look at this graphically, we can see that, let's go red, we can see that these two are inverses of one another, but this is missing. So what we'd have to do is we would have to restrict the domain. We only want to take into account this portion of our parabola. So we would have to say such that x is greater than or equal to negative 4. Okay, whatever this number is goes here, because that's our shift left and right. That way, our half of the parabola is truly representative of only half of that root, the root function.